This time around we're going to take a look at lines and planes in space, or 3 dimensions. So we're going to talk about how to write a set of parametric equations that would yield a particular line in 3 dimensions. Talk about how to write an equation that represents a plane in 3 dimensions. We'll talk about how to find distances between points and planes and lines in 3 dimensions also. So we're going to start by looking at lines in 3 dimensions, or lines in space. So one way we can do this is to use vectors to determine the equation of a line. So we can think of a line in 3 dimensions containing a particular point. So say we've got one particular point on our line. We can think of a line as it contains this point and all the points Q for which PQ is parallel to a given vector. So the vector will kind of orient our line in space. So it'll have a particular point that we want, and then the vector will kind of orient the line containing that point. And that vector will be called the direction vector. Again, because it's kind of telling us where we want the line to point as it contains this particular point P passing through, x1, y1, z1. So since our directed line segment PQ will be parallel to the vector, that means our directed line segment is equal to a scalar times that vector, because that's the definition of parallel vectors, or parallel directed line segments. So with that in mind, let's write our directed line segment in standard position. So to move it to standard position, we'll just take our two points, x1, y1, z1, and x, y, z. We'll subtract them to move it to standard position. So we get x minus x1, y minus y1, and z minus z1 as the components. So here's component 1, component 2, component 3. And since our directed line segment is just equal to a scalar times the vector v, because they're parallel, then our scalar times v will be a t, b t, c t, t being the scalar. Well, those should be equal. So our directed line segment PQ should equal those. So x minus x1 will equal a times t, y minus y1 will equal b times t, and z minus z1 will equal c times t. So if we solve for x, y, and z, we get x is x1 plus at, y is y1 plus bt, and z is z1 plus ct. So this is how we're going to write the equation of a line in 3 dimensions. We're going to use vectors. So again, the idea is we know one point on the line. We're calling it P. So it's x1, y1, z1. That's a specific point. Now, to get the orientation we want, we use a vector that's we want to be parallel to, a vector in standard position. So that way it'll orient our line the way we want it. And since they're parallel, then our directed line segment that's on our line, PQ, will just be a scalar times that vector v. And our scalar, we're using the letter t for that scalar. So since those should be equal, we basically just take the component form of PQ and v, well, our scalar times v, and we set those equal, because they should be equal because we want these two things to be parallel. And then that's how we come up with our set of parametric equations for our line. So basically, if you want a point on our line, you just need to pick a parameter t and then do x1, which is the x-coordinate of our point P, plus a times our scalar. A is the component of our vector, our direction vector v. And then the y-coordinate would just be y1, which is from our point P, plus b times t. Again, t is our parameter or scalar, and b is the component, the middle component of our direction vector v. And then to get the z coordinate of any point on our line, it would be z1 plus the third component of our direction vector times our parameter or scalar t. So let's see this in action. Well, I guess we can formally define it first, and then we'll take a look at one. So our formal definition here are parametric equations of a line in space. So say you've got a line, it's parallel to this direction vector, A, B, C, and passes through a particular point P, which is given by x1, y1, z1. So the x-coordinate of any point on that line will be given by this expression, x1 plus at. Any y-coordinate will be y1 plus b times t, and any z-coordinate will be z1 plus c times t, where t is just some real valued constant. It's our parameter or scalar. Now if we eliminate our scalar, so we solve these all for t and set them equal, then we get what we call the symmetric equations of our line, where x minus x1 over a should equal y minus y1 over b, which should equal z minus z1 over c. So those are what we call the symmetric equations of our line L. So that's just when you solve all three of these for t and then set them equal. Again, this assumes a, b, and c aren't 0, because then we'd have division by 0. Not okay. Alright, so let's give this a whirl. So let's find parametric and symmetric equations of line L that passes through 1, negative 2, 4, and is parallel to 2, 4, negative 4. So this is the point that we want to be on our line, and this is the vector that's going to orient our line in 3 dimensions. So x will be x1. So x1 is right there. This is y1, and this is z1, because that's the point that's definitely on our line. So it's going to be 1 plus a t, and then the y-coordinate of any point on our line is going to be y1 plus bt, and z is going to be z1 plus ct. And then our symmetric equations would just be x minus 1 over a equals y minus y1 over b, and then z minus z1. So these are our parametric, and that's our symmetric equations there. So basically, using the parametric, we just pick a parameter t, plug it in, and get an x, y, and z that's on our line. Pick a different parameter t, plug it in, get a different x, y, z that is on our line. We can do this as many times as we want, getting point after point after point on our line until we are comfortable with where the line actually is in 3 dimensions, and then we can draw that line. So let's actually see this. An idea of what this looks like, actually done in 3 dimensions, since this is hard to draw. Difficult to draw. Okay, so here we are in 3 dimensions. So I've got my direction vector here in this pink purple color. So it was 2, 4, negative 4. So we are below the xy plane. And then our line runs parallel to that. So as you can see, they are parallel to each other. So again, that purple vector is just determining the orientation of our line. And then, so our line just needs to contain whatever particular point we want, and then we orient it with that vector. Alright, so this next one, let's find parametric equations for the line passing through those 2 points. So now we have 2 points, and we want the line that passes through them. So we don't necessarily have our direction vector, although as we know, 2 points do define a line. So let's get our direction vector. So let's create a vector with initial position 0, 0, 0. So we can do that by simply taking the directed line segment that starts at one of these points and ends at the other one, and then just moving it to standard position. So we can do 1 minus negative 2 for the first component, 3 minus 1, 5 minus 0. So our direction vector would be 3, 2, 5. And we can just grab this as point P. We can just have our point P be negative 2, 1, 0. So our parametric equations would be, let's see, negative 2 plus 3t, 1 plus 2t, and 0 plus 5t. So now we can just pick any real number t, plug it in, and get any point we want, or as many points as we want on our line. But what about a plane? What about a plane? So for a plane, we don't really need a parameter, because we can just use an equation that contains an x, a y, and a z, and it handles all 3 dimensions in some sense. So we don't really need the parameter here. So we're going to think of a plane that contains a particular point, x1, y1, z1. So we got some point we want the plane to pass through. It can be thought of as the collection of all points q, so every other point q, for which the directed line segment PQ is orthogonal to a given non-zero vector n, which we're going to have be n1, n2, n3, or abc. So basically, you've got some point P, so you want your plane to pass through that particular point. So a plane is going to be all the points q such that PQ, no matter where you put it, is orthogonal to some given vector n. So if you pick a q that's not on the plane, then they won't be orthogonal. But if you pick a point q that is orthogonal so that PQ is orthogonal, then it'll be in that plane. Well, since vector n and directed line segment PQ are orthogonal, that means their dot product is 0. So if you take vector n, which is ABC, dot directed line segment PQ, comes out to be 0. So basically, component 1 times component 1 here, so A times x minus x1 plus B times y minus y1, and C times z minus z has to equal 0, and out pops an equation for, a generic equation for a plane. Just comes from the fact that the definition of plane is going to be given a point P, it's the collection, the plane is a collection of all points Q such that directed line segment PQ is orthogonal to some given vector n. So formally, the plane containing x1, y1, z1, that point, and having a normal vector ABC can be represented by this equation here. I'm just doing the dot product, where we do directed line segment PQ, make sure it's orthogonal to n by doing the dot product and setting it equal to 0. Alright, so let's find the general form of the plane containing 2, 1, 1, 0, 4, 1, and negative 2, 1, 4. So 3 points to find a plane, 2 points to find a line, 3 points to find a plane. So let's find the equation of the plane containing those 3 points. Alright, so let's grab the first 2 points which would be a directed line segment. So if we have 211, 041 be the initial and terminal point of a directed line segment, let's create a vector representing that standard position. So we can just do 0 minus 2, 4 minus 1, and 1 minus 1. Negative 2, 3, 0. So that's a directed line segment in standard position. We're just going to let that vector u represent all equivalent directed line segments. And then let's create another directed line segment using 0, 4, 1 and negative 2, 1, 4. Let's call that, we're going to have v represent it, so we're going to move it in standard position. So it'd be negative 2 minus 0, 1 minus 4, 4 minus 1. And we get negative 2, negative 3, 3. So we've got these two directed line segments that are in our plane, because we want these 3 points to be in our plane. So these two directed line segments are in our plane. So now we need a vector that's orthogonal to those, and that'll be our vector n. So we're going to let our vector n be a vector that's orthogonal to these two. Well, to get a vector that's orthogonal to these two, we do the cross product. So the cross product of these two will be orthogonal. If we do our cross product, that would be 3 times 3 minus 0 times negative 3 I minus negative 2 times 3 minus 0 times negative 2 j plus negative 2 times negative 3 minus 3 times negative 2k, and that'll come out to be 9i plus 6j plus 12k, or in component form, 9, 6, 12. So this vector u and this vector v, those come from two directed line segments that are in our plane. And then this vector n we now know is orthogonal to u and v because we created it using the cross product of u and v. So now let's pick one of those points. So let's pick 2, 1, 1. We'll have that be our p. So pick any point really, but we're going to pick that point. So the equation of our plane is going to be, we do the dot product of n and the directed line segment PQ, where Q is any point in the plane. So it's going to be 9 times x minus 2 plus 6 times y minus 1 plus 12 times z minus 1 equals 0. And then we can distribute, collect like terms. So you guys can handle distributing. Basically, you get a 9x, a 6y, a 12z, and you get negative 18, negative 6, and negative 12. And collect like terms, you're going to get 3x plus 2y plus 4z minus 12 equals 0. We call this general form. You can divide that whole equation by 3 right off the bat if you want. The number is a little bit smaller. Alright, now let's actually see that. Let's use some software and actually see what that looks like here. So I've got that plane graphed for us here. So remember, we had 3 points that we wanted to be on the plane. 2, 1, or I'm sorry, negative 2, 1, 4, 2, 1, 1, and 0, 4, 1. And as you can see, they all are on our plane, they're located on the plane. And then we did our cross product and came out with 9, 6, 12, and that was supposed to be the vector that was orthogonal to our directed line segment PQ. Q is just any point on the plane, so I've just got Q out here. And we took PQ, we wrote it in standard position, though we moved it to standard position, so that's what this one represents down here. So PQ moved to standard positions right here, and then sure enough, our 9, 6, 2, our vector in, as you can see, is orthogonal. So we've got this particular plane that passes through our 3 points, and our vector in that we created is orthogonal to our directed line segment PQ once it's moved into, both are in standard position. And notice the dot product of in times PQ does come out to be 0. So notice if you were to move Q off of that plane, it would change its angle, making it not orthogonal. That's why we get a plane when it is orthogonal, because it keeps everything level. Okay. So now let's say we have 2 planes that intersect. So got this blue plane here, this purple plane here, they intersect right there. Well, we're going to call theta, let theta be the angle that's between the planes. We'll notice that the angle between the planes would be the same angle if you measure the angle between the 2 vectors in that are orthogonal to the plane. So if these were laying on top of each other, then N1 and N2 would be on top of each other. And then as you move one of the planes off of the other one, those 2 normal vectors move just as much, rotate just as much. So the angle between the planes is the same as the angle between those 2 vectors that are orthogonal to each individual plane. Well, that angle would be given by cosine of that angle theta equal to the absolute value of their dot product divided by the product of their magnitudes. That was from an earlier lesson, the angle between 2 vectors. So if that angle is 90 degrees, so if the 2 planes meet at a right angle, then cosine theta would be 0. Well, if cosine equals 0, then that means their dot product would be 0. So 2 planes are perpendicular if the dot product of their normals is 0. So if vector n1 and vector n2, if their dot product is 0, then that would make cosine equal to 0, making the angle be 90 degrees. If vector n1 and vector n2 are parallel, then the planes are parallel. In other words, n1 would be a scalar multiple of n2 because they'd be parallel. So let's say we want to find the angle between this plane here, x minus 2y plus z equals 0, and this plane here, 2x plus 3y minus 2z equals 0, and then find a parametric equation for where they intersect. Well, let's find the angle first. Let's find the angle between those 2 planes before we do anything else. So we've got this plane here, x minus 2y plus z equals 0. We're which we can think of as 1 times x minus 0 minus 2 y minus 0 plus 1 z minus 0, making this A, B, and C. So vector in this case would be in standard position 1, negative 2, 1. And then for our other plane, the vector that's orthogonal to it, we'll call N2, and it's just going to be 2, 3, negative 2. So cosine of the angle between these two planes, well, let's do the dot product. So that'd be 1 times 2 plus negative 2 times 3 plus 1 times negative 2, and then do the absolute value. Then we'll do the length of this one would be 1 plus 4 plus 1 would be 6. And then the length of this one would be 4 plus 9, 13 plus 4 would be 17. Which comes out to be 6 over principal square root of 102. So we do inverse cosine, and that angle comes out to be about 0.59409 or 53.55 degrees. So the angle between those two planes is just over 53.5 degrees. And then if we want to know, so when they intersect, they'll intersect forming a line. Their intersection will form a line. So if we want that line, let's see if we can come up with a way to get that line. So there's going to be a collection of points that are on both planes. They're on both planes. So say we take the first plane and the second plane's equation. We want an x, y, and z, a collection of x, y, z that solve both, because they need to be on both planes. In other words, we need to solve this system. So if we multiply this top one by negative 2 and add, so let's do a little elimination here to solve the system, we'll get 7y minus 4z equals 0, or in other words, y is 4z over 7. So we'll plug that back into the top equation. So x minus 2y and we get x minus z over 7 equals 0, or x equals z over 7. So notice that y has a z over 7 and x has a z over 7. So we're just going to let t be z over 7. So t is z over 7. So then we'll have x equals t, because x equals z over 7, which we're calling t. And then y will be 4 times z over 7, so that would just be 4t. And then z, let's see, z is going to be, let's look and see. So x equals z over 7, so z is equal to 7x, but x is t, so it's just going to be 7t. So this is these parametric equations define the line that represents where those two planes intersect. So let's take a look at that in some software. Again, it's hard to draw, so Okay, so I've got both planes graphed here. So here's one of the planes, here's the other plane. This one right here is the vector that's orthogonal to this plane. And then this one right here is the vector that's orthogonal to this plane. And we want the angle between those vectors. But we want the acute angle, because basically when two planes intersect, there's two angles that are formed. We have an acute one and an obtuse one, as long as they're not 90. And we want the acute one. So the angle, the obtuse angle is 126.45. We want its supplement, which is 53.55. So basically this angle here is 53.55, which is what we calculated. So the angle between their two normal vectors is 100 and some, but we want the acute angle, which is 53.55. And as you can see, they do intersect and form a line. I didn't graph that part. I figured that part wasn't too hard to visualize. So they intersect a line, and we have a set of parametric equations for that line. Alright, so what about distance in 3 dimensions? So let's say you want distance between a point, say Q, and some plane containing some point P. So say you want the distance, D, between a point and a plane. Point and a plane. Well, so you've got this plane. It's going to have a vector that is orthogonal to it. We were calling that vector N. There's going to be a point P on our plane. So if you want this distance here, well, all we need to do is think of a directed line segment from P to Q, and project that onto N. So if we do P to Q and project it onto N, we'll get this distance, which would be the same as this distance here, which is what we want, D. So we just want to take directed line segment PQ and project it onto N, and we'll get this distance here from P up to this, which is what we want. It's just on the other side of our little rectangle here, but that's what we want. So the distance between a point Q and a plane is just going to be, and it's distance, so it needs to be positive. So we're going to do the projection of PQ onto N and make sure it's positive. Right, we want its length, ultimately, so its magnitude. I should have mentioned that earlier. So we want its magnitude or its length. We want this length. So that's how we know it'll be positive, because when we do magnitude, it'll come out to be positive. So in our projection, we do the absolute value of the dot product divided by the length of this vector here, N. So let's find the distance between this point Q and this plane here. So let's pick any point P on the plane, such as, well, what if y and z were both 0, then x would be 2. So then you could do 2, 0, 0, just to pick an easy point. Now let's do directed line segment PQ in standard position, 1 minus 2, 5 minus 0, negative 4 minus 0, negative 1, 5, negative 4. So in standard position, that is our directed line segment PQ, so extending from point P, which is on the plane, to Q, which is not on the plane, but we've moved it to standard position, so we can write it in component form. Now we want to do the projection of PQ onto our normal, or the vector that's orthogonal to the plane, which we haven't come up with yet. But we can get it from our equation. We just saw that. So our plane can can be written as 3 times x minus 0 minus 1 y minus 0 plus 2 z minus 0 equals 6. So our normal is in standard position 3, negative 1, 2. And we just want to project PQ onto N. So this distance, let's do the dot product. So that would be 3 times negative 1 plus negative 1 times 5 plus 2 times negative 4. And then do a 9 plus 1, 10 plus 4 will be 14. Which is going to be 16 over the principal square root of 14. So that would be the distance. You get a decimal approximation if you want. So basically we found a vector that's orthogonal to the plane. We picked a point on the plane. And we made our directed line segment PQ. And we projected that onto our normal N to get our distance. So going back to our picture, we picked a point P, the Q was fixed, and then we found our directed line segment, but we found it in standard position. And then we found our normal vector N, and we took PQ and projected it onto N. Remember, it's kind of like, so the projection is just the shadow. If you think of this right triangle right here, it's the shadow created by this one onto the leg of the triangle. Well, what if you want the distance between a line and a point, Q? So you've got some line and some point, Q. So here's our point, Q. Here's some line. We want this distance here. Well, that all can be handled in 2 dimensions. So you've got a line, you got a point, so you can create an altitude. Pick a point on the line P, and you have this right triangle. Well, you've got this directed line segment PQ. You've got some vector along the line, and you just want basically the angle between them. Well, just using trigonometry, D is the opposite side of this angle. And there's the hypotenuse, so we'll just get the length of that directed line segment PQ, and sine of that angle will be the distance we want over that magnitude. So the distance we want is just sine of the angle times the magnitude of PQ. But earlier, in section 11.4, so basically, earlier, I guess it doesn't, this section's not particularly important. We saw that in this exact setup, that sine of that angle times that magnitude is really the same thing as the cross product of vector u and PQ, its magnitude divided by the magnitude of vector u. So we can swap that out for the magnitude of the cross product of u and PQ divided by the magnitude of u. That way we don't need the angle at all. We just need u and PQ. So let's try it. So we've got this point Q, we've got this line, there's its parametric equations. So let's create a direction vector for our line. So let's do our direction vector here. Well, in front of T we've got a 3, a -2, and a 4. So there's our direction vector. So let's pick any point on the line. So let's let T equal 0, then you're going to get -2, 0, 1. So now let's create the directed line segment PQ. So we've got this Q, here's our P, so PQ, so this is the directed line segment PQ. And in standard position that would be, let's see, 3 minus -2, -1 minus 0, 4 minus 1. Comes out to be 5, -1, 3. So now we just need their cross product. Let's do their cross product. So we end up with -4 minus, +6 minus 20 minus 9 plus 10 plus 3. And that comes out to be, let's see, 2 minus 11 minus 7. And then we want that length. Which is 174. And then the length of u, vector u, is 29. So our distance is just going to be principal square root of 174 over principal square root of 29, which is principal square root of 6, about 2.45 units. So again, the idea is you've got this point Q, this line here with the direction vector, and this all can be handled in 2 dimensions. So we just make a right triangle. So we drop an altitude from Q to the line, create a right triangle, and then sine of that angle theta, which is between the directed line segment PQ and the direction vector for the line. P is any point on the line, it doesn't matter. We just use our right triangle trig, but we end up seeing that that distance is just sine of that angle times the magnitude of directed line segment PQ, but we don't know the angle necessarily. But earlier, we discussed that in this exact same setup, sine of that angle times that magnitude is actually just the cross product of the 2 vectors forming the angle, its magnitude divided by the magnitude of this one here, u, vector u, forming the leg of the triangle.